Okay, so today we're going to be doing a tarot polynomial and series. And in the do now, hopefully you were able to get the answers from here. So you had to construct a polynomial, p of x. But we didn't know what a sub 0 was, a sub 1, a sub 2, a sub 3, a sub 4. However, we did know that, so we needed to find this out. We did know that p of 0 was equal to 1. So hopefully, just check your work, you plugged in 0 wherever you saw x, and that left you with p of x to equal, or p of 0, also put it in over there, is equal to a sub 0. Well, if p of 0 is 1, then a sub 0 was 1. So we did learn that if a sub 0 is 1, then we have 1 plus. Now, if you were to take the first derivative, p prime of x, okay, then you're plugging in 0 for x. So first you have to find this. And then wherever you saw x, you plugged in 0. This is going to actually help you find a sub 1. Hopefully you found a sub 1 to equal 2, because that was the answer. So you're going to be writing that p of x is 1 plus 2x. And we keep going. So now, hopefully you found p double prime of x, and you plugged in 0. So what this is going to help you find is that a sub 2 is equal to 3 halves. Okay, so hopefully that's what you got, and you plug that in. So p of x is 1 plus 2x plus 3 halves x squared plus. Now, if you found the third derivative, okay, and you plugged in 0 for x, what that's going to help you find is a sub 3. So a sub 3 turned out to be 4/6. Okay, you can reduce it if you want. I want you to kind of leave it for right now. If you reduced it, like I said, that's fine. So you would have wrote p of x equals 1 plus 2x plus 3 halves x squared plus 2/3 x cubed. Okay, so just refer back that this is 4/6. So 4/6 x cubed plus. Now, the fourth derivative, this is notation for the fourth derivative. So if we take the fourth derivative, what this is going to do when we plug everything in for x, then we are going to find a sub 4. So we end up finding that let me erase that. Erase. There we go. A sub 4 turns out to be 5/24. So we're going to say that p of x is 1 plus 2x plus 3 halves x squared plus 4/6 x cubed plus 5/24 x to the 4th. Okay? So you end up writing this polynomial. So a couple things I want to point out to you. One of them is, hopefully the obvious one, is that you wrote this polynomial in ascending order. Okay, that's how we're going to write our polynomials, in ascending order. So the degree of the polynomial, if it's a 4th degree, that's what we're going to be working up towards. The next thing you may not notice, but we actually have an expression that is working with factorials. Okay, so p of x can be written as 1, okay, x to the 0 power over 0 factorial, and 2x to the first over 1 factorial. Both 0 factorial and 1 factorial are 1, and dividing by 1 pretty much leaves those expressions exactly as is. Now, we have 3x squared over 2 factorial. 2 factorial is 2. And 4x cubed over 3 factorial. 3 factorial is 1 times 2 times 3, which is 6. And we had 5x to the 4th over 4 factorial. 4 factorial is 1 times 2 times 3 times 4. That's 24. So all of a sudden, not only are we looking at polynomials that are in ascending order, we're also looking at polynomials that could be written with factorials. And that's something that you see within a Taylor polynomial that we need for a Taylor series. So, I bring up the do now for a good reason. So, going back, it's not the factorials necessarily, it's looking at a polynomial that has this expression to in an ascending order. So going back in our previous lesson, we talked about an infinite geometric power series. And our infinite geometric power series, let's say, is written in this form. Okay. Well, if this converges between -1 and 1, then we know its sum. And let's say for this example, a sub 0 is equal to 1, and it's a power series. So let's say R is 1x. Let me write 1x, or just x. Let me just write x. So our sum would be 1 over 1 minus x. All right, and this is a function. So we can write a series as a function. So that's where we're talking about a Taylor series or a Taylor polynomial. So we can rewrite our series as a function. And this is something we may want to do in order to do approximations. Okay, so I'm going to go into that. So you may have heard me say in the last video about our infinite geometric power series, okay, and how it has a center. And our approximations are going to be within a unit circle for these, because our radius, you're going to find later lessons, that we end up not only finding like our interval of convergence, but what is called a radius. So you can see here that we're going from -1 to 1. That's 2 units. Our radius is usually half of that, so it is half of that. It's not always 1, but our radius is 1, so that's why I had said unit circle. And center is usually 0, 0, but not necessarily. So we're going to come back to that whole concept, but our approximation has to be within here, because otherwise our series may diverge and we're not going to actually be able to use any sort of function to approximate our values. So that's why it's kind of so important to kind of know where our center is when we're constructing a polynomial, as well as the radius. So, like I said, future lessons, but right now, hopefully things are tying together and we can kind of proceed to look at more polynomials, and that's where we're getting to our next example. Okay, so for example 2, once again, we want to construct a polynomial that matches the behavior of at x equals 0 of f of x. And we're going to do this with its first 4 derivatives. So a nice word that's used here is matches. So once again, a lot of times when we're using our Taylor polynomials, you're going to see in our next lesson, it's for approximations. And in order to approximate it, we have a polynomial, and it's usually a curve that gets really, really close to our actual series so that we can get its answer. So if our series kind of goes like this, we want to be able to have a function that kind of matches or replicates that same curve, as opposed to maybe just having a tangent line. Because a tangent line is going to not always be exact, whereas a curve that matches it, a polynomial, is going to be a little bit better. So we say our function's not maybe one of our most favorite ones because ln is our natural log, but we're able to construct a polynomial by using our derivatives, and not just our first derivative, not just our slope of our tangent line. So let me erase this ink and let's get going. Here we go. So we know a couple of things. So f of 0, if we plug in 0 for x, is the ln of 1 plus 0. So this means that f of 0 is going to be 0. The ln of 1 is 0. So this is great, because if f of 0 is 0, okay, and we want p of x, then p of 0 would also be 0. And that's going to eliminate all of these terms, which you already know from doing the do now, because x is 0. So we just found that a sub 0 is 0. Okay, so let's continue and find p prime of x, just like we did in the do now. So p prime of x is going to be a sub 1 plus 2 times a sub 2x. That should be an x. Okay, so this is checking some work you did in the do now as we keep going. So we want to make x equal to 0. And when we do that, we're going to get a sub 1. Well, what a sub 1 is going to equal is what we find f prime of 0. Okay, so let's do f prime of 0. So we need to find f prime, and that's 1 over 1 plus x times 1. And so if we plug in 0 into this expression, we get that this is equal to 1. Well, that means a sub 1 is equal to 1. So far we have a lot of these expressions. Okay, so let's go back to what we're doing to do now. Find double prime. So hopefully you had this there. Okay, so this is p double prime of x. Okay, and we're going to plug in 0 for x, and that's going to leave us with 2a sub 2. Now what this will equal, and I kind of ran out of space, so we had f prime of 0. This will lead us to find p of 0. f of 0 led us to find p of 0. F prime of 0 led us to find p prime of 0. Okay, so f double prime of 0 is going to help us find p double prime of 0, because we're trying to match it up the best way that we can. And again, this is used for approximations. So if we find the derivative of this expression, we then can plug in 0. So if we find the derivative of that expression, we find that f double prime of x is equal to negative 1 over the quantity of 1 plus x squared. I'd probably use the power chain rule instead of quotient rule here, but whatever gets that answer. Then plug in 0 for x. So we end up finding that f double prime of 0 is negative 1. So if I set this equal to negative 1, I find that a sub 2 is negative 1/2. Okay, so we're going to continue on. Okay, the same way we take the derivative of our polynomials, and I'm just going to tell you what the other answers are. So we're not going to take so much time away, especially now we kind of learn from doing this that the more derivatives you have to take, the trickier it is, or the longer the problem's going to be. So let's see, f triple prime of x is 2 over the quantity of 1 plus x cubed. And if this was a 0, then we find that p triple prime of 0 is going to be 2. And p triple prime of x is going to be this expression here. Same thing you would have gotten if you did the do now. So now you end up finding that p triple prime of 0 is 6a sub 3, and that's 2. So a sub 3 is equal to 2 over 6. Now, you can reduce this. If you went ahead of me and you reduced this, that's fine. But remember how I was referring back to these being factorials? So I'm going to not reduce it. The fourth derivative of f with respect to x is going to be negative 6 over the quantity of 1 plus x to the fourth. So if I plug in 0 wherever I see x, then I find that this is going to be negative 6. So I'm going to do the same thing over here. The fourth derivative of p with respect to x is just 24a sub 4. So if I set that equal negative 6, then a sub 4 is negative 6 over 24. Once again, you can simplify that, but I'm not going to because we know that that is a factorial. So what we end up finding for this example, and I know it's kind of all over the place, let's kind of neaten this out and write it. So let me erase this page. That p of x is going to be 0 plus 1x minus 1/2 x squared plus 2 over 6x cubed minus 6 over 24x to the fourth. Okay? We only had to do a fourth degree polynomial for this. And you're going to notice that p of x is f of 0 plus f prime of 0 times x plus f double prime of 0 times x squared over 2 factorial plus f triple prime of 0 times x cubed over 3 factorial plus the fourth derivative of f of 0 times x to the fourth over 4 factorial. If we didn't do a fourth degree, okay, and we kept going, we would say plus ... in ellipses plus our nth derivative of f of 0 times x to the nth power over n factorial. Okay, and we can continue. Where's my factorial? That's the factorial part. It's not letting me write it on this screen. We would probably write dot, dot, dot. I'm not getting my dots on this screen right now. There we go. This is Taylor's series. Okay, now the value of x that we have here, we have a center at 0. So this Taylor series has a particular name for it. It's the Maclaurin series, and that's the only one where it's centered at 0. It's a Taylor series that's centered at 0. So to generalize Taylor series when it's for every center, okay, instead of having an x here, we would say the quantity of x minus c. Sometimes it's an a. It could be an x minus c or an x minus a. So I'm using c for center, but I have used a in the past, depending on which lessons you're looking at. So once again, this is a Taylor series where the center c is at some value. It's a constant a. So we use Taylor series a lot to approximate values of our function. Sometimes it's our natural log, but there are 3 that are very well used on the AP exam. That is the sine of x, the cosine of x, and e to the x. So I'm going to be going over that for you. Before I do, okay, I want to explain why the Taylor series, okay, is used to approximate. Well, we're very used to using the tangent line approximation. And the tangent line approximation can be used to, find the value of a curve. And it's like very, very close. We usually have some sort of point where there's a tangent and maybe we go a little bit off from it for our approximation. And if you look at Taylor's series, okay, and the tangent line, let's take a look at our tangent line form with an initial value of x sub 0 and y sub 0. Okay, our point slope form. Our slope is dy over dx. This is f prime of x. Okay, and y sub 0, if we add that over, is the same as f of 0. So if we were to write our tangent line approximation, we can say y is equal to f of 0 plus f prime of 0 times the quantity of x minus some x value here. Okay, we can use a constant. And let me use the constant of a. That's what it's talking about over here. If you look at just the first 2 terms of Taylor's series, okay, that is your tangent line approximation. So if you have more terms added, more, okay, beyond even the nth term, you're going to get closer and closer and closer to your curve, and that's why the approximations are better and better. And we use a Taylor series to approximate values along our curve. So really super cool that we can do this. But remember, it's for a series, okay, because we're adding up terms. So we have to make sure that our series converges in order to actually find that curve. So that's why a center is so important. And later on with our interval of convergence and our radius kind of comes into play. So I'm hoping that you're excited with all of this fun stuff. And that's really it. I'm going to go into more about like Taylor series and Taylor series approximations with you. So have fun.